This video will work through an MCAT-style passage focused on binding energy, mass defect, and a strong nuclear force. Before we begin, take a moment to mentally prepare yourself. Remind yourself that you are not reading for detail, but for the main idea of the passage. As you read each sentence, look for key relationships or comparisons, and note any relevant scientific background information you've encountered before. Remember that you already have all the knowledge you need to answer every single question correctly. The MCAT is designed to test your critical thinking skills, not how much science you can memorize. With that in mind, let's begin the passage. Good luck, you've got this. So here's the passage. Let's begin. In the past, scientists believed that the mass of an atom was equal to the sum of the individual masses of its protons and neutrons. However, in 1919, the British physicist Francis Aston challenged this long held view with his mass spectrograph experiments. He observed that the measured mass of an atomic nucleus is slightly less than the sum of the masses of its individual protons and neutrons. This difference is now understood as the mass defect, which reflects the binding energy of the nucleus. To describe this discrepancy, Aston introduced the concept of packing fraction. It's defined as F equals ma minus a over divided by a, where ma is the actual atomic mass in atomic mass units and a is the mass number, the total number of protons and neutrons. The packing fraction is therefore a relative measure of the mass defect per nucleon. Aston's discoveries, combined with Einstein's famous formula E equals mc squared, laid the groundwork for understanding nuclear binding energy and the stability of atomic nuclei. Nuclei with a more negative packing fraction are more tightly bound. The following graph represents Aston's results. Here's figure 1. Packing fraction versus mass number for some elements. Question number 1. Why is there such a large difference in packing fraction between hydrogen and helium nuclei? Question number 2. Based on figure 1, which of the following atomic nuclei has the highest binding energy per nucleon? Question number 3. Why does the packing fraction show such a sharp increase from helium to lithium as presented in figure 1? Question number 4. If a newly discovered isotope has a packing fraction close to 0, what can be inferred about its nuclear stability? So after you have read the passage and worked through the problems on your own, come back and we're going to go over the passage analysis together and solve all the problems together. So here's an analysis of the passage. Let's go through each paragraph and point out important information. After you read this passage, you should realize that this passage is about binding energy and packing fraction. So, paragraph number 1, it says in the past, scientists believed that the mass of an atom was equal to the sum of the individual masses of its protons and neutrons. However, in 1919, the British scientist Francis Aston challenged this long held view with his mass spectrograph experiment. He observed that the measured mass of an atomic nucleus is slightly less than the sum of the masses of its individual protons and neutrons. This difference is now understood as the mass defect, which reflects the binding energy of the nucleus. So, this first paragraph introduces the concept of mass defect. It provides historical context about earlier beliefs. It discusses Aston's discovery, explains what mass defect is, and it connects mass defect to its binding energy. Paragraph number 2 describes this discrepancy. Aston introduced the concept of packing fraction. The formula is given, and the various different variables are explained. It says the packing fraction is therefore a relative measure of the mass defect per nucleon. So paragraph 2 introduces packing fraction formula to better explain mass defect. Paragraph number 3. Aston's discoveries combined with Einstein's famous formula laid the groundwork for understanding nuclear binding energy and the stability of atomic nuclei. This sentence is important, this following sentence. Nuclei with a more negative packing fraction are more tightly bound. And then it introduces the graph. So in paragraph 3, Einstein's famous formula is introduced and it is connected to the packing fraction formula to explain mass defect, nucleon binding strength, and nuclear stability. The figure is also shown, which is a graph of packing fraction versus mass number for some elements. The main idea of this passage is that this passage is mostly about packing fraction, mass defect, and binding energy. So the answer to question number 1 is B, but let's see why. The question number 1 states, why is there such a large difference in packing fraction between hydrogen and helium nuclei? So for this question, we need to refer to figure number 1, the only figure in this passage. So as you can see from the figure, the packing fraction for hydrogen is close to 0. And the packing fraction for helium is between -6 and -8. So the answer to this question is B. As stated in the passage, packing fraction relates to how tightly nucleons are bound. Hydrogen nucleus, which only has one proton in its nucleus, has almost no binding energy. So the only proton has no neutron to bind to, which makes its packing fraction close to 0. And it makes hydrogen less stable than helium. Therefore, options or answer choices A, C, and D are all false. D is wrong because one cannot determine nuclear stability based on atomic size alone. The helium-4 nucleus has a very high binding energy per nucleon. It has a large negative packing fraction, very tightly bound nucleons, and high binding energy, and a high mass defect. This makes option B the correct choice. Question number 2. Based on figure 1, which of the following atomic nuclei has the highest binding energy per nucleon? So to answer this question, we also need to refer back to figure 1. It's asking which one has the highest binding energy. So as it was stated in the passage, packing fraction relates to how tightly nucleons are bound. A more negative packing fraction results in a more tightly bound nucleus. This translates into a larger binding energy per nucleon. The element with the most negative packing fraction is iron, Fe. So option D is the correct choice. All the other options show higher packing fractions than iron. Question number 3. It says, why does the packing fractions show such a sharp increase from helium to lithium as presented in figure 1? Answer choice A states the nucleons of lithium experience a larger binding energy, B. The mass defect of the lithium nucleus is larger. C. Helium nucleus presents a smaller binding energy release per nucleon. And D. Lithium nuclei contain additional nucleons that are less tightly bound. Option Answer choice D is the correct answer. And helium 4 has 2 protons and 2 neutrons. This makes it extra stable and it gives it unusually high binding energy per nucleon. Lithium adds an extra proton and neutron, but these nucleons are not as tightly bound. A is wrong because binding energy per nucleon actually drops going from helium to lithium. Answer choice B is also not correct because helium has a relatively large mass defect per nucleon. Answer choice C is not correct because helium has a greater binding energy per nucleon. Answer choice D is the correct answer because lithium contains additional nucleons that are less tightly bound, which explains the sharp increase in packing fraction. Question number 4. If a newly discovered isotope has a packing fraction close to 0, what can be inferred about its nuclear stability? So you have to use information from your background knowledge as well as the information that's presented in the passage to answer this question. For stable nuclei, the packing fraction is negative, which means lots of binding energy is released. If the packing fraction is close to 0, that means the nucleons are not tightly bound, which leads to a smaller binding energy release per nucleon, and this corresponds to the nucleus not being very stable. Option A is not correct because a large amount of binding energy release corresponds to a larger negative packing fraction, not a near 0 packing fraction. Answer choice B is false because a near 0 packing fraction means mass defect is also very small. Answer choice C is the correct answer because a near 0 packing fraction means weak binding of the nucleons and lower stability. Answer choice D is not right because it contradicts near 0 packing fraction. If you'd like to review the concepts, work through additional practice problems, or watch the full version of this lesson, click on the video of your choice here or check the links in the description below. Thank you for watching and good luck on your MCAT journey.